Hi guys, I hope your A2 preparation is going well. I'm just going to do some of these problems from the revision sheet with you guys. So let's start. This is section A, and it says determine the following limits if they exist. Right, so we are going to start with the limit as v approaches 6 from the left of 24 minus 4v over the absolute value of 6 minus v. So let's just write down that limit again. So we have the limit as v approaches 6 from the left of 24 minus 4v over the absolute value of 6 minus v. So let's just quickly look at the absolute value of 6 minus v. So the absolute value of 6 minus v equals 6 minus v if 6 minus v is greater than or equal to 0, and it equals minus 6 minus v if 6 minus v is less than 0. This is 6 minus v if v is less than or equal to 6, and this is minus 6 minus v if v is greater than 6. So in the limit that we have to work out, v is approaching 6 from the left. That means when v is approaching 6 from the left, it is less than or equal to 6. So in other words, we are working with this case. So our limit is going to be equal to the limit as v approaches 6 from the left. And then in the numerator, I'm just going to take out a common factor of 4 so that it looks the same as what we have in the denominator. And we know that we can write the denominator as just 6 minus v without the absolute values now. Then these two cancel, so we have the limit of the constant 4, which is just 4. Just note that if we had to look at the limit as v approaches 6, so it doesn't specify it approaches 6 from the left or the right, then what you have to do is you have to work out the limit as v approaches 6 from the left and the limit if v approaches 6 from the right. So let's quickly consider the limit as v approaches 6 from the right. So then we have 24 minus 4v over the absolute value of 6 minus v. It's equal to the limit as v approaches 6 from the right. Take out a common factor of 4 again. Over. And now, instead of replacing the absolute value of 6 minus v simply by 6 minus v, we replace it with minus 6 minus v now. Because since v is approaching 6 from the right, we know that v is greater than 6. So we have this case here. So our limit is now going to be the limit as v approaches 6 from the right, which is therefore going to be minus 4. So it's important to note here that the limit as v approaches 6 from the right of the 24 minus 4v over the absolute value of 6 minus v does not equal the limit as v approaches 6 from the left of the 24 minus 4v over the absolute value of 6 minus v. So the limit as v approaches 6 of 24 minus 4v over the absolute value of 6 minus v does not exist. However, we were not asked for this. We were only asked to work out the limit as v approaches 6 from the left, and for that our answer is 4. Number B, we have the limit as x approaches 0 of 1 minus the square root of 1 minus x over x. So whenever you get a limit of this form, so in other words, in your numerator, you have something that looks like 1 minus the square root of something. And also in this case, obviously, we can't just put in the value of 0 into x's place, because then we get a 0 in our denominator. What we are going to do is we are going to multiply with 1 plus the square root of 1 minus x over 1 plus the square root of minus x. So we have the limit as x approaches 0 of 1 minus the square root of 1 minus x over x. So what we do is we multiply by 1 plus the square root of 1 minus x over 1 plus the square root of 1 minus x. So when we multiply, what we get is the limit as x approaches 0. Then in our numerator, we are going to have 1 minus 1 minus x. And in our denominator, we are going to have x multiplied by 1 plus the square root of 1 minus x. Now, our numerator can be simplified, so we have the limit as x approaches 0 of x over x multiplied by 1 plus the square root of 1 minus x. So these two x's can cancel. And now if we plug in the value 0 into x's place, we don't have a problem in our denominator anymore. So we can do that. So this limit is going to be 1 over 1 plus the square root of 1 minus 0, which gives us 1 over 2. So that is our answer, a half. Let's now look at the derivatives that we have to calculate. So in number A, we have the derivative of sec squared. So remember, you have to use the chain rule. So this is going to be the derivative of sec squared. Firstly, we have 2 multiplied by sec x. That's the first part. And now we have to take the derivative of sec x, which is sec x tan x. And you can write that a little bit simpler as 2 sec squared x tan x. So that's our first one. For the second one, we have the derivative of x plus 1 all cubed over x cubed plus 1. So here we want to use our quotient rule. So we are going to start, and we have the bottom multiplied by the derivative of the top. The derivative of the top is going to be 3 x plus 1 squared, and then the derivative of x plus 1 is just 1. So we don't have to write it there. Then we have minus the top multiplied by the derivative of the bottom, which is simply 3x squared. And that's all over the derivative of the bottom. Sorry, that's all over the bottom squared. And that's it. Next, we have the derivative of 2 sin 3x plus 1 all cubed. Once again, we're going to use our chain rule. So we have 3 multiplied by 2 sin 3x plus 1 squared. We are not done. Now we still have to look at the derivative of the 2 sin 3x plus 1. This is going to be 2 cos 3x, but we are still not done. Now we still have to look at the derivative of 3x, and that is 3. And we can write this a little bit more simpler. So we have a 3 there, a 2 there, and a 3 there. And if we multiply those, it's going to be 18 cos 3x, and then we still have our 2 sin 3x plus 1 squared. Number D, we have the derivative of the integral from x to 0 of the square root of t squared plus 1. We are just missing a dt there. So what we are going to use here is the fundamental theorem of calculus. Let's write that down. So the fundamental theorem of calculus, or a part of it, says the following. If we have the derivative of an integral from a to x of f of t dt, that is simply equal to f of x. Okay, so we have to work out the derivative of the integral from x to 0 of the square root of t squared plus 1 dt. So the only important thing to note here is that we have our x at the bottom and our 0 at the top. However, in this original one, we have our constant at the bottom and our x at the top. But we can get rid of that problem by simply rewriting this integral and switching our bounds. And we know that when we switch our bounds, all that happens is we have to add in a negative in front of the integral. So we can write this as the derivative of minus the integral from 0 to x, the square root of t squared plus 1 dt, and we can take out our negative in front. So in other words, we can write it like this. And then this is simply going to be minus the square root of x squared plus 1. Number 3a, we have the integral from 0 to 1 of x over the square root of x squared plus 1. So it's the integral from 0 to 1 of x over the square root of x squared plus 1 dx. So we can't just immediately solve this integral. We don't know how to do that. We don't have it in our table of known integrals. So what we have to do is we have to transform this integral so that it's in a form that we know what the answer is going to be. And we can transform an integral by using u-substitution. And we can use u-substitution if we can find some function in the integral. We can set it equal to u. And if we then take the derivative of that function, the derivative of that function is also in the integral. And you can neglect constants when you look at whether the derivative is in the integral. So we're still going to consider those constants when we work out our answer, but when you do the u substitution and checking whether it will work, you don't have to consider the constants. So in other words, if we were to set u equal to x squared plus 1, so u equals x squared plus 1, the derivative of x squared plus 1 is 2x. And we do have an x in the integral. So as I said, when you look whether you have the derivative, you can ignore the constant. As long as you have your variable, that's the derivative inside there, you can use it. So this we can write as du equals 2x dx, which we can also write as 1 over 2x du equals dx. So first thing I'm going to do is I'm going to use this and put it in my integral. So I said u equals x squared plus 1. So I'm going to replace the x squared plus 1 with u. Now I still have my x here, but I want to replace my dx with this. So I'm going to have 1 over 2x du. And those x's immediately cancel. So you don't even have to show this step where you cancel the x's, but I just want to show you guys so you know exactly what's happening. So in other words, what we have is we have the integral of 1 over 2 square root u du. And just remember, you have to change your bounds as well, because your bounds were for x, but now we are working with u. So if x was 0, then that means if we use this, that u is going to be 1. And if x is 1, that means u is going to be 2. If you did not want to change your bounds, that's also okay. But then what you have to do is in your final step, you have to rewrite your integral in terms of x again, so that you can use the x bounds. But it's kind of simple to change your bounds here, so that's what I did. So this is then going to become, let's add in our bounds, the integral from 1 to 2. 1 to 2. So now we have, I'm going to take out a half in front, then I have the integral of u to the minus a half du. Let's now integrate. So I have a half u to the 1 power higher, so it's going to become u to the minus a half plus 1 over that higher power. So it's going to be minus a half plus 1, which is just a half. So just going to write that like that. And it's between the bounds 1 and 2. These two constants cancel, so I simply have the square root of u between 1 and 2, which gives me root 2 minus root 1. And that's the end of that one. For the next one, we can solve this one pretty easily. If you can see that you can just write this as the sum of two integrals, and then we know the integrals of those two individual functions, the individual functions being x and sin 2x. So we can write that integral as the integral from minus pi over 4 to pi over 4 of x dx plus the integral of minus pi over 4 to pi over 4 of sin 2x dx. And we know how to integrate both of these. If you want to do a quick substitution for this, because we know the integral of sin of some variable, but here we have sin of 2x, you can do a quick substitution. So we say let u equal 2x, then du equals 2dx, and we are fine in this case since we said we only have to make sure that the variables in the derivative or in the integral, but we don't have any variables in our derivative, so we're fine. We only have a 2, which is a constant, and this we can write as a half du equals dx. So that means our integral will become the integral from minus pi over 4. Sorry, you're going to have to change your bounds. So we have our sin of u multiplied by a half du. So that's going to be a half sin, a half the integral of sin u du. And since u equals 2x, if x equals minus pi over 4, then u is going to equal minus pi over 2. And if x equals pi over 4, u is going to equal pi over 2. So our integral, the bounds is going to be minus pi over 2 and pi over 2. So we have a half, and the integral of sin u is minus cos u. And it's between minus pi over 2 and pi over 2. So that's going to be a half. Then we have minus cos of u, which is pi over 2. So it's minus cos pi over 2 minus cos of minus pi over 2. And cos of pi over 2 is simply 0, and minus pi over 2 is also 0. So this entire thing is going to be 0. So we basically only have to work out our first part of the integral now, which is going to be x squared over 2 between minus pi over 4 and pi over 4, which is going to give us pi over 4 squared over 2 minus pi over 4 squared over 2. And that is 0. So we have 0 plus 0, so our answer is 0. For the next one, I have the integral of x cubed minus 1 over x squared. So once again, just looking at this, we don't immediately know how to integrate this, but we can write it in a form that we know how to integrate by simply splitting it up into two integrals again. So I can write this as, and I'm just going to do it on this page. I have the integral of x cubed over x squared dx plus the integral, minus the integral of 1 over x squared dx. So my first one, I can just write as the integral of x. My second one, integral of x to the minus 2. When I integrate this, that's really easy. So it's simply going to be x squared over 2 for the first one, and then for the second one, it's going to be minus, and then I have minus x to the minus 1. And what should I not forget? I don't have any bounds. So it's an indefinite integral, so it's plus c. And then we can write that a little bit nicer as x squared over 2 plus 1 over x plus c. For the next one, once again, don't immediately know how to integrate this, but we can find a way to do a substitution once again so that we can integrate it. So I have the integral of e to the 2x over 2e to the 2x plus 3 dx. What I'm going to do here is I'm going to say, let u be equal to this entire thing. So it's going to be 2e to the 2x plus 3. Then du dx is going to be the derivative of 2e to the 2x, which is just going to be 2 multiplied by the derivative of e to the 2x, which is e to the 2x, multiplied by the derivative of 2x, which is 2, and that is then going to be 4e to the 2x. So du equals 4e to the 2x dx. So that means that dx equals 1 over 4 e to the 2x du. So my integral is going to become, so firstly, I replace this thing by what I set it equal to. So I have u. Then I still have my e to the 2x, but my dx I'm now going to replace with this. So it's 1 over 4 e to the 2x du. These two cancel. As I said, it's not necessary to show this step, just showing it for complete clarity, which then gives us 1 over 4 times the integral of 1 over u du. And what's the integral of 1 over u? Well, that's going to be ln of the absolute value of u. But we are not done because our original integral was in terms of x, so we have to make it in terms of x again. So we have ln of u, and u is 2e to the 2x plus 3. And then what should we not forget? Our plus c, because it's an indefinite integral. So our answer here is 1 over 4 ln absolute value 2e to the 2x plus 3 plus c. The final one in section A says if we apply Newton's method on f of x equals x squared minus 3, we get that x n plus 1 equals what? So in order to do this, obviously we have to know Newton's method. So Newton's method says x n plus 1 equals xn plus f of xn over f's derivative of xn. So we have to find the derivative of this function that we are given. So f's derivative of x is simply going to be 2x. And from there it's going to be really simple. So xn plus 1 is xn plus, then we have f of xn, so it's going to be xn squared minus 3 over 2xn. This is the end of section A.